Now let's look at how we would designate a line in a curve in space. A single point can be designated with a vector whose tail is at the origin and tip is positioned at that point you're identifying. So each point corresponds to a single vector. So if we're taking this collection of points, all the points on this curve, we'll use a vector valued function, r of t equal to x of t, y of t, z of t, where each vector and each point on that curve can be designated for a specific value of t. So for instance, perhaps when t is equal to 3, this point is identified as the vector x3, y3, z3. And so that point would be x3, y3, z3, and the vector, of course, that's the components. So each vector corresponds to a single point, and we can use this as a function that defines that whole set of points. Now, notice that the x-coordinate of this vector valued function is given as x equal x of t. And the y-coordinate will be whatever y of t is evaluated for that value of t. And the z-component, the z-coordinate will be whatever this function z of t is evaluated for a given value of t. Now let's look at what's exactly happening here. We've got a curve in space. Every point here is denoted by a vector that's starting at the origin and pointing to it. And now, as t varies, we're identifying a different point on the curve. So notice we're letting the values of t increase. And as the value of t increases, we're getting a different point on the curve, which corresponds to a different vector. Okay, so our first type of equation that we want to define in space, it will be a line. Remember when you were in algebra class and you needed to identify a line, you had to give a slope and a point on the line. That was enough to designate a specific line. Well, for a line in space, we're going to have similar properties. We'll designate a single point, and then we need to give a direction. Just like slope gave us a direction of the line in the plane, we need a direction, and we'll give that by finding a vector that's parallel to the line that we're trying to get the equation for. So if we're trying to find the equation of this line, I'm going to let xyz be just a random point on that line. Notice that this vector p naught, which points to a point here, x naught, y naught, z naught, that's a point on that line, that vector plus some multiple of this v will be this point x, the vector xyz. So for any vector xyz for a point on that line, it will be the vector x naught, y naught, z naught, which is this vector right here. Remember how we add vectors? Tail to tip, and now we put this vector v, so its tail is at the tip, and so the sum of those two vectors will be this. Now that vector v is just giving us a direction, but we know that this vector from here all the way to that point would be some multiple of v. So we'll say it's t, which is some parameter, some value, real number, times the v. So plus t times, and now v V is this vector that's given us the direction of the line. Now they may give us that as just ABC. So they may give us the vector that's parallel to the line, and we'll just use that particular vector. So ABC. So this is our direction vector, which is parallel to the line. We're taking a multiple of that plus that initial point that we know is on the line, and that's going to give us this vector that actually points to another point on that line. So this is the general form for an equation of a line in space. Now you can take this, work with the vector in the component form, and rewrite it as x, y, z equal, now this is just x naught plus t times a, y naught plus t times b, and then z naught plus t times c. Just multiplying the t through and then adding the two vectors. And so this form of the equation of the line, you can think of each of these components as if it's parametric form. So x would be equal, this x right here is equal to this component, x naught plus a times t, y, this component, is y naught plus b times t, and z is equal to z naught plus c times t. And notice in this parametric form, we have the point, that initial point, the x, the y, and the z components, the coordinates for that initial point that's on the line, and then the coefficient of these t's is that vector's components that we know was parallel to that line that we were looking for. So an equation of a line passing through the point x naught, y naught, z naught in the direction of this vector, so that vector is parallel to it. This is the vector form for that equation, where you just say that r, which is a point, a vector that's on that, pointing to a point on the curve, so that would be your x naught, x, y, z. That's your r. And then your r naught is actually that vector that's pointing to the initial point. And then t is just a real number, and then v is that direction vector. So that's the vector form for equation of a line. And you'll see that again if you take linear algebra. And this will be that vector form using the components. Or you can look at the parametric equations where you actually look at the individual components, the x, the y, and the z separately. The x is x naught plus at, y equal y naught plus bt, z equals z naught plus ct. Now, to designate every point on that line, the t values have to go from minus infinity to infinity. So if you want the line to go endless in either direction, let t values go anywhere from minus infinity all the way up to infinity. Okay, I want the equation of a line passing through this point in this direction. So using the formula, we know that r is equal to the initial vector plus t times the vector v. So we'll have 1, 2, 4 plus t times 5, negative 3, 1. And that will give me x, y, z. So we have 1 plus 5t for the first component, 2 minus 3t, or 4 plus 1t. Or you could write as x of t, 1 plus 5t, y of t would be 2 minus 3t, and z of t is 4 plus 1t. Notice, here's our initial point. Spread it, put it, the x, y, and z components, the coordinates with each of the x, y, z equations. That parallel vector, each of those separate components is the coefficient of the t. Now, to visualize this line in space, it's hard to really picture something that's passing through space like that. what we do is we can look at the projection onto the XY plane. Now, if I want to project this line onto the XY plane, that means that we're looking at all the points that are hovering above the XY plane, but that have a coordinate of 0 for Z. So just let the Z be 0, and that means that the X is 1 plus 5t, the Y is 2 minus 3t, and now if we take these and write an equation in the plane using X's and Y's, we eliminate the t. Let's say we do that by, let's solve for t in the first one, X minus 1 over 5, that's t. But then in the second one, t is also y minus 2 over negative 3. Now this is actually called symmetric form for an equation of a line, where you actually just have the equation parts and have them set equal and don't worry about the t value. But this is your parametric form, and that's the one that we'll use most often. Now, let's omit this t here in the middle and actually just write an equation that has x's and y's. I'm going to multiply through by negative 15, so I'll have negative 3x plus 3 equal to 5y minus 10. Now, you can also think of that as cross multiplying. Then solving for y, we have 5y equal to minus 3x plus 13. So that means that y would equal to minus 3/5 x plus 13/5. And that's the equation in the xy plane. It's like the shadow of that line up in space. So now let's say that L is the line that passes through the points negative 3, 5, 8, and 4, 2, negative 1. We want the equation of the line. Well, to find the equation of the line, we know that x, y, z is x naught, y naught, z naught, plus t times the v, which is v is that direction vector. We need to get a v. We aren't given the v in this problem. We can get the v, though, by just finding the vector going through these 2 points. So the position vector would be 4 minus a negative 3, which is 7, 2 minus 5, and negative 1 minus 8. And that gives us the direction of that line. So now, use either point that you want, and we'll have x, y, z equal negative 3, 5, 8, plus t times 7, negative 3, negative 9. That's your vector form. Or simply x equal negative 3, let me go ahead and just write them all down, negative 3, 5, 8, plus 7t minus 3t minus 9t. And this is your parametric form. Okay, so now let's find equations of the projections. The projection onto the xy plane means that the y component, the y coordinate, the z component is 0. Everything in the xy plane has a z coordinate of 0. So just let z equal to 0, and we know then that x is minus 3 plus 7t, y is 5 minus 3t, and we need to eliminate our t. So I'm going to rewrite it in symmetric form. X plus 3 over 7 equal to y minus 5 over negative 3. And now just cross multiply. Negative 3x minus 9 equal to 7y minus 35. So that means then that y would equal to negative 3/7 x plus 26/7. And that will be the equation of the line that's passing underneath. It's the projection on the xy plane. Now let's look at the projection on the xz plane. That means that the y coordinate would be 0. Everything in the xz plane has a y coordinate of 0. So let's take the two equations, x equal to minus 3 plus 7t, and z equal to 8 minus 9t. That's x plus 3 over 7 equal to t, and that's equal to z minus 8 over negative 9. So cross multiplying, negative 9x minus 27 equal to 7z minus 56. So that means if you solve for z, you'll have minus 9/7 x plus 29/7. And that's the projection of that line onto the xz plane. Now, what if you wanted an equation of just a line segment? We just want the part of the line going from 3, 1, negative 1, 4 to 0, 5, 2. We'll do the same thing. We're looking first at the line passing through those 2 points. That line has the equation r equal to r naught plus t times v. R naught is just a beginning point. It doesn't matter which point you use. So I'll use 3, negative 1, 4. I need a direction vector. The vector v we'll get by subtracting, just looking at the line segment, P naught, P1, the vector passing through those, will be negative 3, 6, negative 2, just subtracting the components. And now, notice that if I want to look at just the points on that line segment, I need to limit the values of t. If t goes from minus infinity to infinity, you would be talking about the entire set of points passing through that line, including extending on down in both directions. But if we just want to stop and start at these 2 points, then we need to limit the values of t. Notice, looking at the parametric equations, x equal 3 minus 3t, y equal negative 1 plus 6t, and z equal 4 minus 2t. When t is equal to 0, we actually have the point 3, negative 1, 4. When z is equal to 1, we'll have 0, 5, 2, which is the point P1. So, actually, if we're talking about points here, I need to have parentheses instead of talking about the points, not the vectors. So to talk about any of the points in between those two, the t value is somewhere between 0 and 1. So designating just the line segment, you would have these parametric equations, and you would specify that t went from 0 to 1. If t was 1/2, that would actually be the point halfway between this point to this point. If t was 1/4, it would actually be the point that was 1/4 of the way from P naught to P1, and so on. So every fraction between 0 and 1 gives us a new point on this line segment.